think I'm live. I think it's happening. It's Chill Maths on Twitch. Herb's here. Hello, Herb. Nice to see you in chat. Makes me think that I am live after all. Always good. How's everyone doing today? Hope you're all right. Formula One, eh? What happened there? Oh, it was brilliant. Last week I stopped the stream early so I could go and watch Formula One British Grand Prix. It was amazing. It was absolutely the right call to go and do that instead of doing this. Sorry, chat, but wow, it was great. Hi, Mary and Maths 22222. Good to have you here as well. Don't worry, I'm not going to talk about Formula One. I'm just going to be vague about that. Hi, Neutrino. Good, right, cool. This is exciting, isn't it? Let's point this. And I think we said it as 196. I can't even. It's mirrored. I can't even remember quite what it was. I think we were doing multi-perfect numbers or something, and I had trouble multiplying to 196. Thursday on the Matt live stream, I again had to multiply numbers together like this, 49 and 4, and I told them it was 198. And it's just a second time in my life that I've managed to get 196, like as being the square of 14, just incorrect. Square numbers are hard. Yeah. I haven't got a watts. I don't know. Just the percent symbol. I don't know why. Right, yeah. Oh, I don't know why I did that. So there you go. Go and finish the joke. Go on, do the punchline. Wait, Catherine passed the 6th one? No, like this. Is Catherine passed the 6th one? No. Yes, 6th one and final. Yeah, Survivor. Are you going to do the punchline? Ah! Don't leave us hanging. Welcome to chat. Right. Okay. I have an idea for a kind of... I think it could be a kind of trick question. And I'd like to sort of develop it and test it out on people in chat. So it's a question about a weighted coin. And I need to kind of test it out because I think it's got potential. I think it's got potential as a good trick question. Here's how it works. So I take a normal coin. That has sort of 50% chance to land on heads, land showing heads, and a 50% chance to land showing tails. And to make a weighted coin, weighted coin, I glue a second coin. So a second. I don't want to stress this point too much. I glue a second coin to the head side to make that side heavier. New coin also shows heads. Okay, so now the head side is really heavy because it's got a second coin glued on it. What's the chance that this new object lands showing heads? Maybe I shouldn't have said trick question right at the top. Yeah, let's forget that I said that. Good. Woo. Okay. Here's a question. I've got a weighted coin that I build by taking a regular coin, and gluing an extra coin onto it. So it's now extra heavy on the head side. And there's a guess in chat that it's 50%, which is, I think, the right answer. And then the challenge for chat is to try and come up with a nice succinct reason, like a nice short reason, like why it's still 50-50, or one half. Why is it still 50-50 after I've weighed down the head side by sticking an entire extra coin onto the head side? It's still 50-50. We'll make a wide coin. Let's draw the kind of wide coin that's been constructed as a result of this. Yeah, okay, interesting choices. Good morning, Madnash. Tails is kind of also weighted in a way. Yeah, the new coin is just two half coins joined together. You could think of this as being constructed the other way round, of starting with this one first and then gluing on this one second. I like that way of thinking of it as well. We've just made a very thick coin. Um, and yeah, I like this. I was thinking about this before as well. This idea that coins, maybe in our mathematical model, are infinitely thin anyway. So making it twice as thick doesn't mean anything. And then I got quite distracted thinking about this because I'm not sure if I believe that you can do anything like this to make a weighted coin, because gluing two coins together just gives you a new coin. Can I make it a viral coin flip probability tweet? That would be good. I think I want to do it as more of a physics tweet, but we'll see. Yeah, only land heads or tails, and I think that the way I want it to work as a trick question is that you might think that it's more likely to, this head side is now more heavy because it's got an extra coin on it, so that might affect it somehow. But really, oh no, we've just created a large, thick coin. One coin has a smaller radius. Yeah, okay, so they're different coins. So if I put identical, then it's still a trick question. But then I got thinking about other ways that you might try to make a weighted coin. So maybe the problem here is that they've got the same, they're identical, that the two coins are the same. So then I got to thinking about sticking together, so this is like, oh dear, it's 50%. So then I got to thinking about making a coin with, where you stick two coins together. Coins have got that thing around the edge, haven't they? And you glue a second one on, but this time to make it really work, maybe I make this one more dense or something, or more heavy. I glue these two together. Oh, the art, yeah. Coins. This is what coins look like. They have this bit around the edge, which someone told me once is an Isaac Newton invention. So, but maybe like citation needed. So let's put that on the slide. It's due to Newton, but citation needed. He worked at the Mint for a bit, so it's not completely impossible, but also, yeah. No, it definitely happened. It's true. I've decided it's true. Right. I'm amazed that the person who joined chat to tell me about Catherine Parr has then also tried the maths question and might actually be like a mathsy kind of person who's just because it felt like a weird intro. Okay, so is this loaded? So the thing that I'm worried about, if we stick together two coins with one being more heavy than the other, I'm worried that still won't make a loaded coin or weighted coin, because we've seen that if they're the same density, it's fair, and if the new one has zero density, then it's hard to see it making any effect at all. It would just be the original coin. And if it has really, really high density, then it's like the original one wasn't there, and you're just left with, in the limit of high density, you're left with just the new coin, with the old coin spinning around and flapping around on the outside. So it's kind of like in the limit of zero density, infinite density doesn't matter, and with density equal doesn't matter. It's kind of hard for me to believe that in between it matters. First impressions are important. I suppose something I'm thinking of here is that when you flip a coin, there's actually quite a lot of stuff going on. I don't know if people have thought about this before. Maybe I've thought about this too much. But if you flip a coin, there's a kind of spinning or tumbling stage. Maybe it's spinning like this, or maybe around like this. So there's some sort of spinning and falling. And then there's maybe some some step where the coin hits the surface that you're flipping it over. And if it's a hard surface, then there's maybe some sort of bouncing going on, followed maybe by some sort of step of, maybe later on you get something a bit more like rolling or tumbling. And then as it settles down, maybe there's a step where it kind of falls over or something, like a toppling sort of stage where the coin is, maybe just balancing on its edge or something for a moment as it slows down, and maybe could sort of topple, and then finally some sort of settling down stage. There's some really cool dynamics for this last bit of how it maybe continues to spin as it's settling down. There's something called an Euler disc that I think you can just buy them. A sort of special metal disc that is not even that special, but it's like a metal disc and a hard surface. As the coin settles, there's this kind of precession wobble thing. The contact patch migrates around the edge faster and faster and faster. I've seen Steve Mould do good videos about that. So there's sort of so many steps. You might hope that maybe these last steps don't affect which side is showing at the end. But maybe you might think that the kind of rolling, tumbling side, maybe the kind of weight distribution matters. And I'm going to put a question mark on this because who knows? And you might think in the bouncing, maybe it matters. I think the weight distribution actually doesn't matter while it's spinning and falling, which is maybe a bit of an audacious claim, but I think during that bit, the weight distribution, what do I think? I think it just spins. I don't think while it's falling, it will tend to have the heavy bit down or something, because gravity doesn't need the heavy bit to be down. Wolfoloff in chat is rotating about the centre of mass. When the position of the centre of mass, on the one hand, the coin is very thin, so the centre of mass is just in the middle. If we could off-balance it or something, but I can't really see the point. So if we're doing rotationally symmetric coins, then the centre of mass is kind of in the middle. If it's got thickness, then you can start to talk about whether it's near one side or the other, which maybe matters in like the toppling stage if the centre of mass is really near one side. If that is a real stage of it sort of rolling and bouncing onto its edges. Vivi says in chat that we should just assume it to be perfect in weight and only view as an example of probability. And I suppose it is the mechanics that I'm getting into here as well. What's the parabola of probability distribution? Is that a thing that... It's not a thing I've heard of before, maybe. Bread with jam always falls with the jam side down. So anyway, I think... What can I do on the chill math stream then? Probably not mathematically model most of this. Watching Steve Mould videos on this. Steve Mould on YouTube has got some great stuff on Euler disc spinning. I think Matt Parker might have got involved with it a little bit at one point as well. At least Hugh Hunt as well. Surprisingly complicated because there's this contact which might be slipping, and there might be friction, and there might be stuff going on with the bit of the disc that's also rolling and rotating. A lot of stuff. Okay, so chat's going. Probability. If the added one is infinitely dense, will it not be the 1-0 thing? See, if the infinite one is very dense, then the thing is that for the falling bit, the actual mass doesn't matter because the actual mass cancels out in Oh, is this true? Ah, is this actually true? What can you affect? The position of the centre of mass matters, and I was going to say mg half mv squared. The mass cancels out, and then I remembered about moment of inertia, and now I want to think about moment of inertia a bit, because the spinning maybe gets affected by those two bits having different densities, or am I overthinking it? Really depends how you model it and where you put them, I think, in terms of the flipping over, which is the bit we care about, maybe. Think of badminton. So maybe I should admit that at the moment I'm really not thinking about air resistance. So in badminton, I'm pretty sure that the air is really, really important, and that helps. That causes the rotation of a shuttlecock. There's a mention of badminton in chat, where that provides a kind of torque. That's very complicated. I guess I'm hoping that changing the density of the coin doesn't affect its aerodynamics, but could be wrong. It might be the case that a very front-heavy coin is unstable as it's flying through the air and wants to. Back-heavy? It might be the case that a very back-heavy coin is unstable and it wants to flip around to fly through the air like a shuttlecock would. The shuttlecock, for people, I've said the word a few times. I'm going to try and draw one. That'll help, won't it? Me drawing something is going to help a lot. I guess I felt like that was. I don't know. I said it a few times, and then I thought, no, we should try and draw this thing as well. Not an art stream. I regret because I like colouring in. One of those. These turn around. Weighted dice definitely exist, don't they? So how do I fit that into my? How do I fit that in? Dice. So dice do a lot of rolling. Is that relevant? But how do I believe? So I suppose there's lots of steps here when you roll a die. Maybe the spinning bit. It could be the case that the spinning and falling through the air is unaffected by the weight distribution. I'm not sure that's true, but it could be true. And then it could still turn out that, once it starts hitting the ground and rolling, it's more likely to end up on a particular side. Does squashing it ruin the effect of a weighted die? I don't know. Oh, I've never seen a name on that as a theorem. It's a theorem. Oh my goodness, I'm learning today. A mathematician I haven't heard of. I've never heard of this. Thank you, Fluff. Here's a kinematic theorem. Ooh. The most general rigid body displacement can be produced by a translation along a line. Oh, okay, this. Rigid body. Every Euclidean motion. Oh, okay. Am I doing Euclidean motion now? I've got an acceleration due to gravity. I suppose that's a different displacement. What are we talking about? Talking about where the thing is. Good stuff. Yeah, something like this. There's also a different one. Ooh. One side would be drawn more to gravity, so it would slow the spin down. Let's see if I can do this weird. There's this weird proof that I half remember. That it's something like conservative force can't exert a torque on a system of particles. I can't quite remember how this proof works, but I'm going to give it a go anyway. I can't quite remember what the statement is, but I'm going to give it a go anyway. So it's something like you've got a collection of particles. I think it's from this bit of maths where you've got a collection of particles with positions xi and masses mi, and they exert some forces on each other. You know, maybe they're joined by complicated springs or gravity or sticky glue or something. They exert forces on each other, so sort of internal forces, Fij, and that's like the force on I due to J or something. There's like a whole bunch of internal forces. Newton's third law, Fji is equal to minus Fij or something, equal and opposite, whatever. But there's also maybe some external forces that act on each particle, which I need to give a different name to. What am I going to call them? This is going to be a big problem if I give them a stupid name. I'm going to call them, the letter after F is G. I might regret that. I'm going to call them G. I, for the force on each one of them. Now there's some stuff you can do with this. This is a very general setting for when you've got a system of particles with lots of forces acting between them, to talk about how the thing is sort of made of particles that are springy maybe, or doing complicated things. But overall, perhaps we can say something about, I don't know, the centre of mass of this overall cluster of stuff. So that the idea being we could then do physics like you've got a tennis ball that's flying through the air. Tennis ball's very complicated, lots of moving parts, but its centre of mass does something predictable. That kind of feels like maybe it should be true. You can do some calculations for this, which I'm going to try and do from memory. This has become a sort of chill maths, sort of semi-improvised theorem proof someday. Yes. Okay. Here's what I think is true. Yeah. So for each particle, if you're doing Newtonian motion, which you probably are, is something like, so mi xi double dot for the acceleration of that particular particle is, well, something to do with all the forces acting on that particle. So that there's that external force, and then a big sum for all the forces due to everything else. So let's sum this over all the j for all the other particles. Force on I due to all of the different particles j. And that's Newton's like F equals ma. Here are all the forces, including all the complicated internal stuff and that external force. Okay, I think we can add these together. So the centre of mass is at some position x, where I think the idea is that what's true about the centre of mass is a point x such that, now the way you find the centre of mass is something like you add together a weighted distribution of where all the points are, as if you're trying to replace them with one weighted average, such that, so over here I want sum of all the masses times x is equal to the sum of, and then on this side, the calculation that you might actually do to add up for each particle, tell me where it is and how much mass is there, add all of those up, and then kind of divide by the total mass. People sometimes call that capital M, don't they? And that gives you the centre of mass. You could do dynamics for that. So you can work out what's going on if you differentiate this with respect to time. So if the masses are all constant, and I guess you could do something clever if they're not, but let's keep it nice today. So differentiation is really nice. It respects sums of functions. So you've got all these different functions, right, for the positions. But differentiation is really nice with a sum. It just differentiates each term. So differentiating twice, lovely. You just get this double dot inside. And we have a rule for what that is, that this is the sum of R over I, and then in here, so it adds up all the external forces and adds up all the internal forces, but, each internal force has an equal and opposite reaction. This Fji is equal to Fij minus Fij thing. So I think all of this cancels. I can't be bothered to do this properly. No, I should split up the sum, I think. Split it up to cases where I is less than j, cases where I is bigger than j, do the bijection between those properly, but it's chill maths, so just gonna say that cancels. That cancels. Okay, so far so good. This tells you that the dynamics of the centre of mass just depend on the total mass and the total external force. That's good news. Even if your tennis ball is sort of squashy and it's oscillating because you gave it a really big hit and it's wobbling around, and also all of the bits of the tennis ball inside are bouncing around connected to each other, the centre of mass of that thing moves like a point mass would, which is really handy for your dynamics. That you have all this complicated stuff going on, all of these different particles interacting with each other, but all the internal forces cancel out when you do that sum at the bottom. Give you this dynamics. This is good for us because we've got, for our weighted coin, two particles really glued together. And I don't really want to think about the forces from each one of them on the other one, but because the overall force cancels out, you can talk about the dynamics of the centre of mass. Okay, that was the easy bit. Because you kind of knew this, right? That things behave following the centre of mass. The centre of mass moves, even if the thing's spinning or doing something weird, right? I reckon you knew this already. I think I want to talk about rotation. So I want to talk about the rate at which it's rotating, which is, oh my goodness, going to be a pain, isn't it? So what's my half-remembered fact? My half-remembered fact is that if you look at the amount of rotation and you try to work out how the angular velocity changes, then you might get something from the external forces, but the internal forces can't create. The internal forces cancel out again if you're thinking about the kind of angular acceleration of this cloud of points. I've got to define angular momentum, I suppose. We've got some momentum going on here, haven't we? If you do angular momentum by taking the cross product of lots of things. Yes, I'm taking some cross products with velocities and cross products of velocities and positions weighted with mass, probably, and some of those. Yeah, and then ask the question, what's that doing over time, or something? That seems like a sensible question. And sort of do dynamics for that. Talk about how that's changing over time. And the internal forces cancel. And then I think the punchline is that the external force also cancels if it's constant. Maybe better than that, but if it's constant, then everything's just accelerating and there's no torque. So if the force is constant on each point, then you don't get a twist, even if some points are heavier than others. My angular momentum. I guess I'm going to try and prove that it's conserved, even if there's external forces, which isn't true in general because you could have like your weighted coin and I could give it a push to set it spinning, which wouldn't conserve angular momentum. But for some sorts of force, like gravity, maybe it'd be fine. Maybe that'll help us distinguish like the badminton case, where in the badminton case there's some force from air resistance, which is not constant, it's different places. Centre of mass relative to the position of particles also changing. Yes, if they all... They can do anything. They can do anything. These internal forces could be really weird. They could do anything. The way you calculate it stays the same over time. Oh, Maths 222 is giving me a decimal snake. Is it the thing that you made last week? Yes, it is. I did see this last week. I should come back to it. It's good. Thank you for making it. I also worked out how to colour in areas, but yes, area colouring it. We'll do that next. Because it's dual maths, I'm going to do a little bit of trying to work out what on earth I'm talking about, but quite casually. So if you want to tell me about something else, I'm open to distraction. Open to the idea of being distracted by something better. That areas graph is good. That's in the queue. What is this? So this is a sum because I think there's a chance that this doesn't go anywhere. And it's actually quite boring. Do people like mechanics? I'm not really sure. I like mechanics. Ooh. This is 10 is 0. And we know a fact about MI acceleration. We know that this thing in here is like the sum of Fij and the Gi's, these forces, cross Xi. I think this is what I want, because then once again the Fij stuff is going to cancel out because, oh no, oh no. There's no way to show the internal core. Oh no, Wolfilov says I should stop. I need to introduce rotational Newton's third law. Oh no, I think I've got to that point now, look, because I wanted to say they cancel, but I don't think I can. What am I doing wrong then? Am I supposed to do the angular momentum of like the rotation about the centre of mass? I should stop trying to remember this, I think, and go and look it up. I think I've done enough to imply that, there might be something going on if you have some reason why. Yeah, so these are not going to cancel, are they? These G's crossed with the X's. Because the X's could all be over there. And then the thing's falling. And yeah, okay, so it's not just angular momentum. I need to do rotation about the centre of mass or something. Because a tennis ball, if I have my if I have origin over here and the tennis ball goes flying over, then its angular momentum changes because it's going up and then it's going down again. So I've got something wrong. So I need to do it relative to the centre of mass. Okay, right, fine, something like that. Good. Take a 3D space, then have a Einstein. Use a transformation matrix to turn it into a situation where it looks like a coin, but the plane doesn't change. Yeah, okay. Do I even believe the dice exist? I think it comes back to bouncing. Right, good. Thanks for joining in while I do not very interesting content on weighted coins. They came up on the Matt live stream a few weeks ago because we were talking about probability, and I realised that I can't think of a way to build one where I can think of a way to build something that might be a biased coin, but I don't know if I can explain why it would be. Anyway, last week after we were live, I set homework-ish for people to do something with areas. We had this Desmos plot with area in, and my plan was that, as a reminder, this is a curve with some parametric definitions and sweeping out an area as it moves. We're integrating y with respect to x, but x changes at different rates because as we change, it's down here somewhere, the curve is f of t comma g of t. As we change t, the amount that f changes when it's different at different times. And what I wanted was, you see that bit where it comes back again? That's kind of negative contribution because, well, y is still positive, but dx, y dx, but dx is now negative because we're coming back again. And I set that as homework to try and make it colour in red so that the total will be purple for the overall contribution. Maths2222 in chat has gone and done that, so well done. This is now an illustration of how some positive bit of area and some negative bit of area. There's a bit over here as well, so we can test this initial stage. It's moving left, so we get this kind of red negative contribution to the area. The nice thing that happens is that, this is really good, there we go, okay, and then it comes back again, wow, nice. Comes back again, and the nice thing that happens is that it exactly cancels out the bit under the curve, so it goes left, and there's some stuff underneath, and then it goes right, and the bit under here cancels out the stuff under the curve, so you get the stuff inside the curve, or the curve doesn't quite have an inside, I mean, it's not a closed curve, but if you joined up the curve along the y-axis at the end there, you could say that's inside the curve that you end up with, which generally happens. Anyway, now that Maths2222 has built this, we can look at other curves, we can look at other stuff. So in particular, I can do things like this. Yeah, looking forward to this, I think it's going to look good. And then this can go all the way up to 2 pi. Yeah, there we go, okay. So you can do this negative, positive, negative area stuff. yeah, so this is now a nice little demo of negative and positive areas. So if you want to show someone, oh, you're getting some negative contribution there, and then you're getting some positive contribution shown here in blue, and then it comes back down again, you're still getting some positive contribution though, and then you get some negative contribution underneath, which you know from doing integration. And in this case, they all cancel out because the reds and blues add together. This is this kind of cancellation idea. There's maybe this way to think about it that I tried to talk about last time, where it's kind of got blue on one side and red on the other, and as it goes under, you're seeing the other side. Because this has been coded nice and generally, we can do all sorts of stuff involving it going forwards and backwards, right? Like, so weird stuff like this with cycloids to think about the area. Where here I'm now playing with the X stuff, so you can kind of see these vertical lines for the amount that X is changing as we go through. So I think this is good. The one I really wanted to do is some sort of circle. We get a circle in here. So X, I would like to start at. I would like X to start at 1 and come round. I would like Y to go like sine. Yeah, so this one surprised me a bit. Yeah, this way around. So what happens here is that as we go around, we're going left to start off with. So we get some red negative area, and then underneath, it comes around the back, underneath, and we get red underneath. We get some negative area, because now it's moving right, but the value of the function is negative. So for that bit, we get some negative contribution. So we end up with this entire circle filled in red. And in fact, if you go and do the integration, y dx, but change dx to dx by dt, you go and do the integration, you get exactly the area inside the circle. So this is a way of calculating area. Let's say I just did some integration out loud, which is, I think, not advised. The thing we're doing is like y dx using this, because everything in the question is given in terms of t. So if you go and do that integration, I claim that you get the area inside a circle. I could probably go and check that, couldn't I? This is x cos t, this is y, and the claim is that if you integrate sine t dx by dt, sine t dt from 0 to 2 pi, well, that's minus sine squared. Sine squared has average value 1/2, so this is minus pi, which is the area. Oh, up to a minus sign, because it's red. So I really like this. Thanks for making this maths 22222. You took my Desmos and added the colours in, which I think really helps. If I flip it, blue, flip it twice, red, flip it the other way, blue, red. Okay, and it's actually a general fact that if you integrate y dx around a closed curve, then you get the area inside. Let's see, can we do like the area inside a squircle or something like this? Can I take what do I want? I've currently got it set up so that x squared plus y squared equals 1. What do I want? X squared plus y squared equals 1. I'd like to do something fun, like x to the 4 plus y to the 4, for which I think I need the square root of cos. Oh, it's not going to like this. Well, let's try this first. Oh yeah, don't know what I was expecting to happen. Oh, yeah, okay, not my greatest work. Can I make this fun? Oh, that was almost good. It's like one corner of a squircle. Where's it only gone to there? I've upset the I think I've upset the thing that shades underneath. It's got a little bit of a trick to not get crossed by the ends. Thank you. There's some sorting going on. Good. As I have said a couple of times, I made a basic version and then Math22's put all the fun stuff in. Yeah, so if you had a favourite shape that you wanted to find areas inside, then this is an option. There's some cool stuff, isn't there? If you do, why am I getting all of these wrong? I want to do something like one of those, one of those squircle things in all 4 quadrants. It's not being very nice to me. I think what I'm doing is silly because of how cube roots work. And, oh, no, I haven't gone all the way. So coming back again, and then going a bit more red, and then going a bit more blue. Great. The sorting makes the colours constant when overlapping. Huh. Oh, so that it's not sometimes red over blue and sometimes blue over red? Or is the sorting doing, what order they render in or something? Oh, well. That's just me. Back to me flailing around trying to make this do the... Yeah, that sort of thing. That's what I wanted. This. But go all the way. Yes, there we go. Start. We do more? More so? Yeah, make it more so. Cool, and then if we... Ooh. Lips. Then if we wanted to start, if we wanted to find the area inside here, maybe I should integrate around the other way to get blue. Desmos is okay, right. Thank you, Maths222. Gosh, that's the sort of bug you don't want to have to fix. We'd have to do some other sorts of integration, wouldn't we? I get not other sorts of integration, but we might end up with a whole bunch of trig functions inside here. So it says if x is minus cos cubed and y is sine cubed, then our formula would be x is, I've already forgotten what I said, x is minus cos cubed, y equals sine cubed. Then all we'd have to do is sort of this. Sine cubed, I guess I should use t since that's the variable we're using. Dx per t is another sine, with a minus sign cancels the minus sign, and number 3 and cos squared. That's not too bad at all. That's the sort of thing that people can integrate. Sine to the 4t cos squared t. Good. I think this is the sort of thing we might make students do this in multivariable calculus or something, at the point where they learn this kind of integration, that there's some relationship between the integral over an area and an integral around the outside, which is kind of what you're doing, right? You want to add up the size of all the squares inside. That's an area kind of question. And there's something you can do around the outside, which is just this single parameter t going around the outside, something to integrate. Suggestions for sine to the 4 cos squared? I think I'll probably... What would I do? I was going to say just replace the cos squared with the 1 minus sine squared, and then look up values of sine to the n. Can I be cleverer? Yeah. This is cos. Y is 4rt 1 minus cos t to the 4. X is cos t. Is that a curve that we should put in? What's the suggestion? No, I'm going to skip. Wait till the 4 is inside. Ugh. Ugh. Welcome to chat. Animal. Is that Curur? I don't know. I have no idea. Oh, 4-3. I'm being silly. Oh, you're making a squircle for me. Welcome to the stream. If you've just joined us, we are. What are we doing? I don't really know what we're doing. Just messing around with Desmos, really. We've got a thing that draws areas. Happy animal. Okay. Welcome to the stream, Happy Animal number 1. We are chill maths stream where we sort of mess around with Desmos, learn about integration in this case. We've got a tool that takes a parametric curve and shows the kind of area underneath it, in blue if it's positive and in red if it's a negative contribution to the area. So you can make them kind of cancel out to get this kind of purple colour that has this kind of cancellation going on in the middle. So this kind of shows me that if I integrated y dx for this function x and this function y from 0 to 2 pi, then it would all cancel out and I'd get 0. But that says something about the function, I think. But there's a minus sign in the cos somewhere. Like if you integrate it this far, you get the area of a square. Because I see what you've done. Maths 2 in chat has been very helpful and has rearranged for me cos to the 4 plus sine to the 4 equals 1. So I have an expression for y. Good. Okay. Visualizations of area. I'm sort of thinking about how to do this integration. I have a silly idea. Yeah, here's a daft idea. I bet this works. So if you take one of the sine squares, you can write this as like this. I'm going to forget about the 3 for now, and maybe I shouldn't. Whatever. Okay. This one's a bit easier, and this one I claim is the same as the one we started with. It's also sine to the 4 cos squared, but shifted by pi over 2 or something. But that's okay because we're integrating from 0 to 2 pi, so I reckon these are the same. So I think what we want is 3 over 2, 0 to 2 pi of sine squared cos squared. And that's just sine 2 theta over 2 squared, which I reckon, so 3 over 8 and then sine squared integrates to pi. I reckon it's 3 pi. I reckon it's 3/8 pi. Should give it to Wolfram Alpha. How do it integrate? I mean, these suggestions are wild. Wolfram Alpha is always very keen on the suggestions. Let's go x. Quick but wrong, I think. Oh no, pi by 8. Quick and right. Okay. Oh, backed up. I didn't put the 3 in. My laziness knows no bounds. Arbitrary amounts of lazy. Oh, good. Right, claiming that as a stream win. Coming back from a really dodgy, really rough bit of mechanics where chat had to intervene to tell me the thing I was trying to remember isn't even true. We've come back with a quick dub. Sine to the 4. Take one of the sine squares to switch this to the other side. No integration by parts, just switching one of the sine squares to relate it to this similar integral. These are the same, so divide this by 2. Yeah, sine squared cos squared I've done before. I'm always trying to get my students to get faster at integrating sine squared. Let's have a quick look at sine squared. Let's use our new tool. It feels a bit like using 1% of the power of this visualization thing. So sine squared looks like this, and here's the area underneath. It's blue because it's positive, I guess. It's nice how that works out. The thing that I'm always trying to get my students to do is to recognize that this function is kind of very symmetric around 1/2. Look, that's symmetric, but without the blue boxes, the black line is very symmetric around that curve. I mean, if you sit and do the working out, you know that sine squared is somehow related to cos 2 theta or something. Like you could work out it's cos 2 theta plus 1/2 on that first thing's over 2 or something. There's some relationship between something with higher frequency than sine, but oscillating around 1/2, which means that if you only want to go up to to pi or something, or even just up to pi, then this top bit of area is just going to perfectly cancel out with these missing bits here and here. So you're just going to have 1/2 times the kind of interval that you're integrating over. And this is true when you go up to 2 pi or 1 pi or 3 pi. It's also true if you offset it a little bit. So if you go from something like this, then it still just perfectly balances out. It's kind of speed run way to get the integral under sine squared. I'd really like my students to see that. I should show them again. They're not watching. Maybe we need a bingo card for the stream with something like James vaguely throws shade at Oxford students. Yeah, exactly. It's thank you, Neutrino. It's 1 minus cos 2x over 2. Yes. And the thing that I want them to do is that the cos 2x over 2 bit, well, if you integrate that, then quite often it cancels out when you plug in the limits. And if you can see that coming, then you can save yourself loads of time, because integrating 1/2, really easy, don't even write anything down. Integrating cos 2x over 2, only for that bit to turn out to be 0. We got other things we could be doing. We could be doing actual maths. That'd be nice. So, you know, there's a few moments in the Oxford course where they have to integrate something, and my main, trying to get them to do that without worrying too much. So I found a step question that's a bit like this. Where's it gone? There it is. This is something of a classic, because Stephen Siklos tells a story about this step question, where the fact at the end was kind of known but maybe forgotten about for a long time, until Stephen Siklos rediscovered it and used it for a step question. So it's kind of like forgotten maths or something. He's got a post about it somewhere, I think. Not sure how I'd find that. Should maybe have dug it up before we went live. Anyway, the actual fact is brilliant. You have a general curve, and you have a stick of a particular length with a point marked on it, split with distances a and b, and you just run that around the edge of your shape. Then you get some sort of weird curve on the inside as that point moves around, as you slide this around here. And the area in between those things is always pi AB. Even if the outside thing is very complicated, the inside thing is very complicated. You always get pi AB at the end, which is sort of really weird. I'm not even sure I can do that for a circle. Maybe we should try that. Let's try this for a circle first. Just to illustrate this. So you got a circle. That's one of the worst circles I've ever drawn. That was not much better. This thing's got a circle built in, right? There we go, okay. Circle. Forget this one. No. Okay. Circle and straight line. Okay, haha, who needs GeoGebra when you've got online whiteboards? Everyone. Okay, so for a circle it's not very fun, because as the stick or whatever slides around the outside curve, it's just rotating, because the outside curve is the same all the way around. So the only thing I need to calculate is this distance. Do I want this distance? Yeah, probably want this distance, because it's going to stay over there. This feels like all of those. Oh dear, this feels. I'm in Geometry Town. This is prime opportunity for people in chat to tell me that, aha, you can work out this distance just using power of a point. Should I maybe have set the radius of the circle? Should maybe have set the radius of the circle. Yeah, well, it's going to turn out not to matter. Yeah, exactly. There they are. Maths tutor, the intersecting chord theorem, the thing that I've forgotten. Now I have to go and look up the intersecting chord theorem, and if I do this really sneakily, then people won't know that I don't know what that is. Just realising that you're in. Oh yeah, okay, it's one of those geometry things. Oh my goodness. Is it on GCSEs? No. I mean, it's in Euclid's Elements, so I should probably have known it. That's not the bar I should be setting for myself, really. Ah, it's this thing, power of a point. What is this? So if I want this distance here, and this is the radius over here, and this is radius minus d, then apparently the intersecting chord thing tells me that r plus d, r minus d is equal to AB. Intersecting chord theorem. You got some chords that are intersecting. For me, one of them's the diameter, but fine. Okay. Why is that true? I should probably know this. Anyway, intersecting chord theorem gives you r squared minus d squared is AB. And then beautifully, if you multiply both sides by pi, this gives you the area of the circle minus the area of the new thing that you'll get as this goes around. It's pi AB for the area in between. Yeah, and r plus d. So I had a radius over here and a d, and then r plus d. Prove it using vectors? Yeah. Prove it using coordinate geometry. That would be fun. Just to intersect lines and circles, right? How bad can it be? Wikipedia tells me that I can. Oh no, I don't have Wikipedia up. I already know what this is. Wikipedia says that you can prove with similar triangles, which sounds like a fun challenge. Inscribed angle theorem. Let's have a look at that. Apparently, this is in GCSE, so I've forgotten more maths than I knew. Learning maths from Wikipedia. Let's go. Flashbacks to so much geometry that I should know. I've got distracted by geometry. Here we are. Right. There are only 3 lines. How hard can it be? Yeah, but I did GCSEs more than a few years ago, so it's not an excuse for me, is it? Okay, let's go. Here's the kind of 4 points for your intersecting chords. You mark in the quadrilateral. Okay, I know facts about quadrilaterals. Now, what are they going to tell me? ADS. Oh, those are going to be similar. Wow. ADS is BCS because those are on the same chord over here, angles, and DAS and DBC are the same because, yeah, okay, same reason, looking at that bit over there. And then the other angles in those triangles match up. Now, are they equal? ASD is BSD. ASD is BSD. BSC? Oh, opposing angles. Oh, that's 3 lines, not 2 lines. Nobody's claiming that those 2 angles are equal. Oh my goodness. Okay, so you got similar triangles, and therefore the ratios. Oh, the ratios, and then it all works out. That's it. There are 2 other versions before you get to power of a point theorem. Oh no, the ratios of the sides. Right, okay. Ratio there and the ratio there. Okay. Oh, right, okay, so it's just lots of angles being the same because of one of my favourite facts, that inscribed angles over a chord are equal. Painfully familiar to neutrino. Like, genuinely forgotten it. I've not just forgotten learning this, but forgotten like knowing it or doing anything with it. Except the phrase power of a point theorem is something I've heard of. So just everyone in chat already knows this. So just forgetful person relearns GCSEs with a Twitch audience. So is that what we're doing? No, we're still going. We're 1 hour in, which means it's time for a cup of tea. Thank you, Neutrino, for redeeming channel points. Tea time applies to people watching chat as well. If you want to go make a cup of tea, I'm going to go make a cup of tea. I'm going to run an ad, and I'm sorry in advance, but if you can deduce it every time, there's no point. I couldn't deduce it. Not clever enough to deduce it. Not rememberable enough to remember it. I make a cup of tea, and I suggest other people do. I'm going to run an ad because I've realised that we're getting quite close to the point where this stream cashes out and actually donates to charity. So this is a reminder from the distant past. This is a permanent charity stream where we're raising money for the Sutton Trust. We donated the money in advance, but it would be nice if we actually got to the target. So I've realised that's getting close. And if I run an ad, then maybe we get very close. And it would be really fun if that happened at the same time as that happened, or everything lining up. Not in the sense of like, oh yeah, we're going to cash out and this is going to get me money. Like, we get to actually donate to charity, which is donate. I guess the sequencing is something like there's a fence post error kind of thing going on, right? We pre-donated and then we do the stream, and then we do a donation. But actually, that's kind of for the future of what's happening next. But I still want to run the ad now rather than the future, even though the donation was in the past. Untangle that one. See you in. See you in a minute or two. I think an ad's about a minute and a half. Let's find out. Back in a minute. So many countdowns. I'd forgotten about all the countdown timers. It's quite stressful in a way, having all of the... I say this every ad break, but when you run an ad on Twitch, it starts a timer, and then it starts two more timers, and I guess. People joining the stream for the next half an hour don't get pre-roll ads, so that's nice. But do I need a countdown for that? It's only 5 minutes until I can run another ad break. Right. Oh yes, Mary has received all of the adverts. Well, this time only 3. It's not too bad. Thank you, Mary. Has Herb, I need to know. I know Herb got no adverts. Herb is usually shown an advert for a BMW, which, you know, when I press the button, I always think, see if Herb will buy a BMW this time. That's not what I think every time. Beeping. Weird power to have, right? Beep. There you go. Oh, just tennis. Are you buying? Yeah, okay. Expensive habit, but it's for charity, so that's all right then. There's a point where I should probably say thank you to Neutrino, who's been, as I hover over, a subscriber for 8 months. Thanks to Neutrino, that is. Also going towards the thing I mentioned. And if anybody's used a Prime sub, which I think is an Amazon Prime thing, if you have Amazon Prime, you can use an Amazon Prime subscription. I cannot remember what that gets you. You get something like, I think you get access to some emote thing or extra channel points. I don't know. Neutrino, do you get any benefits from being a subscriber? You're allowed to say no, I won't be offended. I mean, you can say no angrily if you like, and then I might have to create something. No ads, right? Which means you were looking at the words back soon for like 2 minutes. Okay. So that means Neutrino would like it if I ran more ads with maybe secret content at the same time. Is that what I should be doing? Is that how you like monetize this thing? So I have like secret. I actually tell you the answer to the integral, but only during an ad break. So you're too busy looking at the BMW. No? Oh, Mary, yeah, okay. There was the dynamic that I don't want, by the way, is the dynamic that I don't want is for some of the viewers to feel not special. Is that it? You just get 20% more channel. You get no ads, and you get 20% more channel points. a thing which you use only to tell me to drink tea. Twitch, eh? What a time to be alive! What a time to be alive! I can learn power of point, and so can you at home. In a live stream setting. Yeah. Right. Ooh, okay. There was someone in chat. Someone told us to keep doing geometry, so we're going to keep doing geometry for at least a bit. It's better than dynamics in terms of stream potential. Yeah, I didn't lock any emotes behind subs. Yeah, I thought about doing that. I haven't actually created very many emotes, have I? I've only got 2. Oh yeah, I got fed up. I was going to create loads of emotes. I remember now. Emotes, yes. Lovely latex symbols, but they all got banned. And then I got a bit nervous about creating. I created a lot of banned emotes in quite a short time, so that was. It turns out, rereading the rules, you're not allowed to have an emote that is a single letter, so that people don't spell things. So I should have seen that coming before I tried to create a symbol for the real numbers as an emote. I just thought it'd be useful. Utility emotes, right? You could follow this channel and then get utility emotes to use on Twitch. But I've not been keeping up with how they work. Anyway, I should probably create more emotes. You've seen the quality and craftsmanship that's gone into the 2 existing emotes. You know, you can't just pump those out. They've got to come from really from the heart. Right, what are we doing? The power of a point. Yeah, see? A little face. Oh. The power of a point. With respect to a circle with center I and radius r is defined by you square the distance and take off the square of the radius of the circle, which is an incredible measure for whether you're outside or inside the circle. That is all. Thank you for coming to my TED talk. Have you considered squaring the radius? I think we on the spectrum, I guess all we're missing is like a kind of middle option, which you can currently express by not posting in chats. Like neither the empty message is kind of the third. Yeah, what are we talking about? We have 4 because you can post both, 1, or neither. That's the 4 experiences. Bing, massive like. Twitch gave me like a massive flashing light, like a big green. What could be so important that it gets my attention right now on the dashboard? What could it be? What could it be? Oh, I have permission to run another ad break. That's what Twitch is. That's what Twitch wants. Show them the cars. Show them the cars. Confused would be useful. Let's get on the list. Oh, I have a confused face. Do we not do this one? Do I never do this one? Of like the kind of wobbly face? I can't remember if I've done it recently. The confused face, which I think is not an actual thing. I don't know where I got this from. Do other people use :S? Is that a real, like... At one point I tried to look up a list of, like, emoticons, which is what those are called. I use :S quite a lot, but I'm not sure it's a real thing. Anyway, we'll see. Okay, right. Back to the TED Talk about power of a point. I've never really... I must have been to a dozen talks about power of a point, you know, in my teenage years, and then trying to recreate learning geometry. I must have been to like a dozen of these. I never really got anywhere with it. Let's see if I can do it now in the context of a live stream. Yeah, and there is tea. Thank you, Neutrino told me to do it. Right, starting to use this to prove loads of stuff. Ooh, I like the problem of Apollonius. Okay. Yeah, alright, okay. Points with, hang on. Points with equal power are circles concentric to circle C. Yes, because the only thing that changes is PO squared. Yes. We had a maths club about power of a point. Anyway, never mind. The power diagram. Ooh. Well, that looks like more power diagram of 4 circles in computational geometry. My favourite. It's more generalised. Oh, in the case that all the circles have equal radii, it gives you Voronoi diagrams, which I love a lot. I'm not going to read this now. Wikipedia, focus. Wikipedia and focus don't really go together. Let's find out what we've got. Right. For any point outside the circle, there are 2 tangent points on the circle C which have equal distance to P. Yes. Hence the circle O with centre P through T1 passes T2, 2, and 6C. What are we doing? This is just some geometry facts, right? Oh wait, no, it's actually good. Oh wait, no, it's good. It tells me where to put it. Or what the radius should be. Yeah, okay. The circle with centre P and radius that intersects C, the original one, orthogonal. We seem to be alternating quite a bit between lowercase. Oh no, we're using lowercase for the circles now. Uppercase? No, we're lowercase over here. Never mind. Okay. Right, what's going on there? Quick think. So if you set the radius to be the power, not a concept that I was thinking about. So you've got this kind of... If you said, aha, I can see a Pythagoras. I said, okay, I get it. If this thing over here is power of the point or whatever, which is... Wait, no, maybe I don't get it. Oh, yeah, if you set this to be the square root of this, which is the square root of PA squared minus R squared, I forgot the square root, then Pythagoras, we're all okay? I shouldn't have squares on these sides. The radius is just R. The distance is just mod PA. What am I doing? I took a good Wikipedia page and copied it out badly. Understanding is hard, isn't it? Okay. So if and only if the radius is the root of the power, root of all power, then you have orthogonal intersections. Good. Otherwise, cosine rule, good. Oh my goodness, what's going on here? Right, intersecting seconds theorem, intersecting chords theorem. For a point P outside the circle, and intersections points S1 and S2, the following is true. But the product of those distances, P to S1 and P to S2, is the power of the points. And then the intersecting chords theorem, which we just had, that the product of those is not only equal for two crossing chords, but there's an expression for it, minus power of the point, independent of the line G. Independent as the product is independent of the line G over any point. That's a good fact. No, actually, I do like this. Okay, I've got my goal. I would like to understand this. I think that's my target. Yeah? Yeah. Yes. Right. We sort of just did this, but no, I didn't understand that it was the power of the point. So I'm imagining. Yep, okay, common proof down here. Good. I would like a common proof. Is that common in the sense of regular or common in the sense of. Oh well, never mind. Oh look, vectors. I was warned about these. Chat told me there would be vectors. Arbitrary unit vector. P big point. The parameters T1, T2 have possible common points on the line. The circle we can determine by intersecting. This is kind of parametric stuff I was expecting. P plus TV vector minus r squared. Why is there a minus r squared? What are we doing? Oh, to be on the circle, you need to have the size of that vector needs to be r squared. But if you expand it out, then you get all of this. Yep, seems good. Mod p squared in here. So when you see vector squared, I think we're supposed to imagine the modulus of that vector squared. You know, it's a good definition, I guess. Oh my goodness, what is this? From Vieta's theorem, one finds T1 dot T2, and the product of those things is the constant on here, power of the point. Oh, well that's nice. Oh. Well, that's nice. Where did that come from then? So that last bit, TV, oh, mod V is 1, so this is just T1. There's a T squared in here, which is just mod V squared on the front. Okay. So, that works really well. Right, okay, so chat, look at this. We've got a vector for where these points are. We don't know what direction we're going in, but if you find these 2 points as the 2 solutions for T, they satisfy a quadratic equation, which I guess you're intersecting a line and a circle, so you were expecting a kind of quadratic equation to come in there somewhere. But it's nice that you can just work out what it is in terms of that vector v, but then that doesn't matter because it only affects the middle term of the quadratic. So it doesn't affect the product of the roots. Okay, so when I see this, I should think of this as the product of the roots for a distance to there. And those distances, the product of the roots satisfies that term on the end. I should try and think about the quadratic equation in my head when I see the secant's theorem. That's going to be hard. We'll give it a go. You see a circle, you see a line, you think, aha, quadratic equation. What are those distances? Well, those distances there's distances over there. You could write them as vector from P plus a little bit, the size of that as a vector from the origin, the size of that would have to be r squared, but it's, on the other hand, it's something to do with P, which is constant, P squared, and there's a constant on the end there, the quadratic. You only need to think about the coefficient of T squared as you move along the line, and the coefficient of the constant coefficient, which is the fixed thing, that P is fixed. So whichever direction you're in doesn't affect the constant on the end. Ugh. I think I can almost imagine multiplying out that quadratic. Let's practice on the chord theorem, where it's the same idea, isn't it? And the algebra is on the screen if you want to just read the algebra. Is it literally exactly the same? But now the roots, one of them is positive, one of them is negative. Yeah, so why is it not exactly the same then? Mod v is 1 is the following statement for S1 and S2. What is that? It's just the power. This is still defined to be the power even if we're inside the circle. It's just negative. Oh. Why is it this? T1 and T2 have different signs. Oh, the actual length, the actual distance might not be T1 or T2. The actual distances are always positive. So there's mod T1 and mod T2. So if you want to do a geometry fact about the distances, you're not telling me about the parameter T, really? You're telling me about mod T? That's irritating. Okay. So it's whether those distances, kind of morally, there's a bit of a negative distance in here. I've previously set chat the challenge of talking about negative areas. Now I feel like I found a negative distance. Are you with me, chat? Like it's in the opposite direction. So you've got this kind of positive thing over here, and you've got this negative thing over here. We know that the product of those things is the power of the point, but oh no, in geometry we say that that is positive distance, not a negative distance to get from P backwards, because what direction would be positive and what direction would be negative, I guess. The distance has the useful property of being rotation invariant. The product of those things, I guess we know the product of those T values. In here it would be negative, but we just want the moduluses. Okay, so it's a bunch of moduluses because geometry asserts that distances are positive. Fine, okay. I can deal with that in my life as well. Or displacement, not distance. Yeah, there you go. Negative distance. Chat is not happy with that concept. Good. But do you not feel like we have a beautiful statement about the product of the T values? It's always mod P squared minus R squared. That's always true. And then there's this kind of case stuff going on, like in some cases power, some cases negative power, because we've got this like convention that we always say that these things are positive. I think we've lost the kind of beautiful true fact in there. I'm teasing a little bit. One of the reasons that I worked on the area picture for Desmos is that I'm actually quite happy with the idea of negative area. I think things are just better if you accept in your heart that areas can be negative. It has some counterintuitive results, like the area inside a figure of 8, the total area inside a figure of 8, which we can parameterize now. The total area is kind of 0 for me because half of it is backwards, but that's not what people mean. If you define area to be precisely the thing that's easy to calculate, then everything's nice, because it's easy to calculate. If you define it to be what we've been doing with that area picture, then everything's fine, and not that much goes wrong. Not that much. Let's try and can I draw a figure of 8? Am I clever enough to do a figure of 8? I would want something like sine t. So I'd want y's. I'm imagining the y's going up and down, and x going up and down twice as fast. That has not worked at all. 4 times as fast? No. 3? Onto something. 1.5? Why has that done that? Oh, it's lined up. I want to go round and back. So I want x to go 1, 2 oscillations, and at the same time I want x to do this over 2. I'm so confused. Just stick it out of phase. No. Yay, figure of 8. Okay, so figure of 8. Oh, goodness me, has this worked? I think I've drawn a figure of 8. We've got some negative areas there, and then we've got some cancellation, and then we've got some more negative stuff over there, and then some cancellation. Yeah, red plus blue is not the same as blue plus red in Desmos. So all of these bits are actually kind of purple and they've cancelled out. Red plus blue, not the same as blue plus red. Interesting, investigate Desmos. But then you've got this big red bit and this big blue bit, like a perfect hourglass kind of thing, and I kind of feel like they should be different and cancel as well. So the total area inside your figure of 8 might be 0. I mean, if you integrate around the edge, that's what you get. Of course, if people just show you if people just show you the hourglass and they want the area inside, that's probably not what they mean. But partly, I think it's that double red. I think it's just red and blue. Or is that one double? No, I think it's just red then blue. Curve's only drawing stuff over there twice. I think that should be some blue and some red. Actually, I've realised this top one is red then blue as well. Or maybe then is not quite the right word to be using. It's definitely ended up with a different colour in here, which Maths 222 mentioned at some point about being a kind of... There is something that Desmos does weirdly with colour stacking. Somewhere in here, I saw that you were doing some... Oh no. Doing some clever colouring. Okay. Anyway, negative distance, not a thing. Right, okay, so when I see a point and a circle and I want to intersect, then the product of the distances might be the power of the point or negative power of the point. Think about whether it's inside or outside the circle, whether you've kind of got a negative distance involved in there. And then there's all of this. People who know about this sort of thing, is this good? Is this something I should read? Looks complicated. Oh, homothetes. Oh, I've seen that word. Sort of thing you should maybe do. Similarity points are an essential tool for Steiner's investigations on circles, says Wikipedia, with a citation and everything. And the citation is to Steiner, so you know, let's respect that. So similarity points. If you have two circles, gosh, this the sort of thing where somebody told me once that it's just. I think someone told me once that this is all just projections from sort of 3D geometry projected down onto the plane. And some of them, if you do it in 3D, it's much more obvious why stuff's true. I don't know if this is an example where things are more obvious in 3D, but we've projected out to 2D. Okay. So, what the data map? C1 and C2 stretches the radius. As the centre Z on line M1, M2. What are we doing? What are we doing? These different pages. Yes, they are. They're scaling, right? With respect to some point. Okay, good. Yeah, and then I. So what's the idea here? You can scale up your circles. There's some red point, which is sort of the origin of the scaling. You could probably work out what that is, given. I guess that's what we're doing here. Yeah, okay, that's where it is. Exterior. Oh no, that's what these are. Oh, and then these are. Oh, the green one also does the same thing, but it's kind of like taking a circle and scaling it in and it comes back out the other way around, or something. Okay, that's cool. I like that. Oh, new graph. Oh, it's fixed the thing. Oh, that's so fast. You got the reds and blues. Only one person in the world, I think, understands Desmos colour, stacking colours on top of other colours, and it's Maths 222 in chat. So there we go. Hello, Lashoma. Hope you're doing well. Happy stream. We've got an areas graph like last time. User in chat has just shared a better version that has all colours and reds and blues and purples. This works beautifully. Doing good stuff for this kind of cancellation. So if we just integrate out to there, maybe if I change the minimum down a bit like that, then I could find the area inside this kind of hourglass bulb. I think I want to double this. There you go, yeah, that'll look really good. There you go, figure of 8. I knew I could work out how to draw a figure of 8. If I just tried a bit harder. Desmos really struggles if you give it 3 things to stack on top. Too many things, right. I love that little dinosaur emote. That's so good. It's so happy. It's doing such a little dance. It's doing its little dance. For people who've just joined, like last streamer, you didn't have to watch an advert because we ran an advert. We ran adverts. We do that sometimes when we remember. We've been learning about, not that, we've been learning about this concept called power of a point, which takes the, for any circle, you can work out the power of your point by squaring the distance to the origin and subtracting the square of the radius. It's a measure of whether you're inside or outside the circle or not. But also, it's related to some nice theorems about intersecting lines with circles, which I think I was supposed to know a minute ago when we were trying to do a question up here. Yeah, so it would have been handy in this question because I would have said, aha, these distances A and B, they multiply to the power of the point, which is d squared minus r squared. And then I would have got to, oh no, minus that because we're inside the circle. There we go. They multiply to give negative the power of the point, r squared minus d squared in this case. And that's some fact that I could have had. Rather than worrying about what I actually did, was I went and did a Google search for intersecting chord theorems because somebody in chat told me to, and then I applied that very sloppily. So power of the point lets me just write down the fact AB is equal to r squared minus d squared, which I can sometimes write down correctly. We did that because we were trying to think about this step question, or at least look at this step question, which has got this kind of cool fact that, okay, it's true for circles that the annulus you get is always the same, no matter what. Oh, it's always the same function of A and B, no matter how big the circle is. It's kind of surprising, maybe. Doesn't matter how large the circle is. In fact, it doesn't matter what the curve is around the outside. And the step question has this definition of area. It starts with this thing from A level or equivalent. I think maybe further maths, but I'm not sure, for area inside a curve with polar coordinates. I suppose this expression is where I wanted to get to. Just wondering whether I can do this step really quickly, just as an example. I think I maybe can, because this is just, where am I going to get this minus sign from? That's going to be a problem, isn't it? So x squared is x squared plus y squared. This is what you do when you're doing area with polar coordinates. And now I'm going to really struggle, aren't I? Because obtain the equivalent expression this with all the x's and y's mixed up. That is a strange one. Oh no, theta. Yeah, if you know about the Wronskian, then there's something going on here. So I guess it's going to come from changing variables between theta and t, which, do I want to do that? Not sure. Let's have a go. How bad can it be? So we're trying to change variables so that we're doing our integration with respect to t. So there's kind of a substitution in a way, related by tan theta is y of t divided by x of t. So if you hit both sides, you get sec squared theta d theta by dt, which is just what I need for this kind of switch. I'm going to rewrite that d theta as d theta by dt, and it's equal to quotient rule on the right hand side. The thing in the question divided by x squared, no dots. Quotient rule. Don't let me down now, quotient rule. Sec squared here is, I think it's all going to be okay because, it says nervously, sec squared is something like 1 plus tan squared. Have I got that right? Yeah, I've divided by cos squared, haven't I? 1 plus tan squared, which is 1 plus y squared over x squared, to theta by dt. And then I'm okay because this is going to cancel out. This 1 plus y squared over x squared multiply it by x squared, divide by x squared plus y squared, and I get to theta beta t is, I think, precisely what I want it to be. X squared plus y squared down here. Sorry for the messy handwriting, because then this d theta, I can rewrite it as y dot x minus yx dot dt, kind of, divided by x squared plus y squared, which cancels out that x squared plus y squared and just leaves me with all the stuff in here. Ugh. So here's a different expression for the area. And I want to be clear that this term here with the y dx by dt is the thing that we've been doing to calculate areas for these parametric curves. We would just calculate this and then worry about minus signs and not divide by 2, but the divide by 2 is just there because this expression over here also gives you a definition of area. It gives you, sorry, the same, I don't mean definition, it gives you the same values. It also calculates the area. So this is two different ways of calculating the area, added up and divided by 2. Not for any particularly deep reason, I think. It's just quite a nice expression. Symmetric in x and y, almost. Switching x and y puts a minus sign in it, because switching x and y turns all of the areas over to the other side. I don't know how to explain that if you don't believe the area. I mean, once again, I'm faced with the idea of explaining the areas. You're going to just turn them over and you get a minus sign. That happens when you go past the x-axis, and also happens if you're inverting right to left instead of left to right. You get all these red areas in our pictures. Anyway, there's an expression for the area, and apparently it's only one step question amount of work to parameterize where these points are, and then write down all these areas and just prove that the area between is pi AB, which sort of sounds quite fun. I think I might have a go at that. We've got 20 minutes, which is not really long enough for a step question, but I think that's my plan for the next bit. But as I say, I'm open to being distracted by other things to do in chat, which is how we got onto geometry, I think. Yeah, it's a winding road on the chill maths stream. I'm just going to do this step question, I think, because I've never done it and I would like to know why this fact is true. It's a good fact. I'm going to clear some space. Right, okay. So coordinates of A and B in terms of A, B, X, Y, and T. So if you're given the point P, then A and B are at, it's T the angle. I wasn't paying attention. The angle between AB and the positive X direction is T. Point P is fixed distance A. Point fixed distance B from B. The angle AB is T. As A and B move anti-clockwise around C, anti-clockwise, the angle T increases from 0 to 2 pi. Okay, that sounds true. I mean, we're given that fact. P traces out a convex curve D inside C. I wonder if that's why we're told it's convex. Anyway, let's not worry about that right now. So, I think I want to add on B cos theta. I think A is at wherever P is, plus some sort of correction term to allow for the rod. And for B looks like the easier one to talk about. Add on B cos T and B sin T. And A looks like I should subtract A cos T and A sin T to work out what those points are. Okay, I've got expressions now. I assume the question is now just plug those things into your areas calculation. Yep, show using star, which was this. I've written all over the star, but x dy by dt. Does this work then? I guess x is changing with time, y is changing with time as the point P moves around the curve. I don't know how it's changing, but I've got a formula for the areas. Yeah, okay, well let's just plug it in then. A, B. So what do I actually want to plug in? The area is swept up by OA, OB, and OP. So A and B should be the same because OA and OB are both going to sweep out the area of this curve. So these are equal. That's why there's no B in this statement. P is the thing swept out by OP. So this thing here is just going to be 1/2 of whatever we add up here, x dy, yeah, x y dot minus y x dot dt. That's what area P is. And then these things are equal, so I'm only going to do one of them. I'm going to think about how. Well, this has only got a's in, so I think I'll take the a, and that f on the end is some horrible integral. Right? Okay. Maybe this is not that bad or something, but we'll get there. Okay, so I'm going to work out a just by plugging in. Now the formula has x and y in. For me, those are slightly modified, but you know, I'm just going to sort of plug it in, trying not to think too much about what I'm doing. Y dot, so differentiate this one, minus a cos t, and there's a minus sign, and then it's time for some y coordinates, and x dot, a sine t, plus sign in there, dt. So hoping that we get quite a lot of the same terms. I can see some things coming back again. Are we integrating from 0 to 2 pi? I reckon we probably are, as t changes. Right, so we're parameterizing, and this is a bit weird, but we're parameterizing points on the curve by the angle that the line would make with t, which I'm being clued to do because these are functions of t up here. And it's not the obvious thing to do when you have this set up, is to parameterize the points on the curve d. You don't know where the curve d is yet, given the curve c, but to parameterize points on that curve by the angle that the line would make with the x-axis, and to think about that changing from 0 to 2 pi. So I put 0 to 2 pi on here. I should put 0 and 2 pi on the other one as well. Okay, not obvious, and you know, tricky way to set up the problem. Okay, so the first terms from the brackets are just definitely going to give me p. I can kind of see them, the first terms in the brackets, but there's a bunch more that I'm worried about. Let's work out the other terms. I'm going to ignore the cross terms for a moment because I can see an a squared cos squared and minus minus and a squared sine squared, which I can deal with, and that's going to give me the 2 pi over 2 a squared, so I'm happy with that. I'm trying to do them in order as well, look. And then there's, yeah, a bunch of terms that depend on a. So I'm going to go plus a over 2. Maybe I should do minus a over 2 to match the thing in the question. Integral from 0 to 2 pi. So I've got my over 2. I'm going to bring out all the a's because there are all these cross terms, right? Minus, and I can see x and a cos t, and minus. This is where I'm going to make mistakes, I think. Plus x dot sine t. And then if I'm lucky, this matches up with the thing in the question and we can move on. So this is x plus y dot, lots of cos t. I have a minus sign in the middle, so something to worry about. And y minus x dot sine t. I've got several minus signs wrong. It looks like this one I've got wrong. And it looks like I've got this one wrong. Those come from, where do those come from? Tricky, they come from quite different places, don't they? They come from this minus cos t term over here. And this term over here. How have I done that? How have I got that wrong? Am I somehow actually correct, but with t going the wrong way or something? Like one big minus sign. If I do a substitution, t goes to minus t, then that changes overall a minus sign, and it flips. I say it'd be x of minus t. It would go the other way, so put a minus sign here and here from the sign, and maybe also here for that sign. So I'm not going to, and maybe here in the time derivatives. So one here, and here, one here, and one here. So maybe I've parameterized this the wrong way round. Maybe I've got the position of A wrong. Would be bad. Chat's gone very quiet. I think chat likes it when we do step questions. Maybe I shouldn't have assumed that these would be the same because we're about to do an expression with a b involving the letter B. I know, I assumed they'd be the same, right? I think Can I follow that through at the end? Could it be consistent? That if somehow both of them are equal to this. No, that'd be daft. Oh, idea. Okay. For the corresponding expression of B, have I not understood this properly? I took the negative out this front, but then forgot. That would be classic me. That's good advice. Thank you, chat. Yeah, why did I try and take that minus out the front? That was a bit ambitious, wasn't it? Okay. Yeah, okay, that explains some of the minus signs, doesn't it? Because there's a minus here on it. These cross terms are just negative. I'm just wrong. Yeah, cool, good. I think I was, okay, so it was closer than I thought. And then this term, this y sign has a minus on. But I should have brought that out and put plus, I think. And then, yeah, okay, I only took the minus sign out the first term. Because then this x dot sign has got minus minus on it, but I pulled a minus sign out, so I should write minus. Okay, pulling the minus sign out, not a good idea. My eagerness to make it match the given expression stopped it from matching the given expression. I really do think these are the same, but how am I going to show that? How am I going to convince myself that's true? The area swept up by OA. After 2 pi, it's got back to where it started. It swept up the whole thing. The area swept up by P. I really think square brackets around A and square brackets around B are the same. Is F the same in both cases? Oh, is it not quite? Is it maybe plus AF? Ah, has B maybe got exactly the opposite signs on it? With a B? Question mark. So when I do this for B, it's like replacing all of the A's with negative B, which is going to flip the signs here and here to give me this. But the P stuff will still be the same. Now, I really should think about the area swept by OA and OB. Are they the same? I almost don't want them to be the same because it'd be nice to have an expression with P in it and a separate expression with P in it where the P's don't cancel. But how am I going to get pi AB out of this? Oh, yeah, they're not going to cancel, are they? The area between them, I would like. Okay, the area between them is not mod P, square brackets around P. The area between them is something like this. Not B, which we have an expression for. Pi A squared minus AF. And also maybe it's pi B squared plus BF. I think, because there's also more B. So what's going on? You got 2 expressions for this thing. Can I calculate F? That'd be good, wouldn't it? Calculate F and be done. I think I'm being hinted not to calculate F. This is, after a factor of A, this is pi A minus F. And after a factor of B, this is pi B plus F. So what do I think is true? If this really is pi AB, then is this pi B? And this is pi A? Oh, yeah, right, okay. We're going to eliminate f. We're going to eliminate f or something. These things are equal. Mod A and mod B, size when you sweep out A and size when you sweep out B are equal. I should write down an expression for that. I should actually do something with that fact. And I want to eliminate f because I don't want to calculate f. Yeah, and if I do that, actually writing it down is a good idea because then I get A plus B, F. I get something like this. Not quite sure I'm going to get all the plus and minus signs right, but you know, we try. Here's F like this, pi A minus B, and then take the fact, use that to eliminate F. So I don't want to calculate it, just put it back in. So then the difference here is just pi A squared minus A pi A minus B, and it's going to be perfect. It's going to be absolutely perfect because the pi A squared is going to cancel out. We're going to get minus pi AB as required. Not bad. We had 20 minutes. We've still got 10 minutes left. Not bad at all, I think. This question is so good. So it's a big horrible integral. But if A and B both sweep out the same area because it's going all the way around, so OA is sweeping out this area, and so is OB, then you get these two different expressions that both involve, because A and B are very similar, they're on different sides of the point and there's different lengths in there, but you get very similar expressions for this horrible integral thing. Then it's true that, yeah, exactly the same exact integral appears, but you can make it cancel out by doing the algebra to it. What a good question. For any curve, parameterized by, well, so okay, there's some, now maybe we can understand the terms and conditions, right? It's closed so that you can go all the way around without falling off the end. And convex, that's interesting. What goes wrong if it's not convex? Oh, do you get into a point where there aren't, you get into some points where your AB stick, there's kind of no such points that exist? Huh. That's interesting. Well, this point goes outside? Yeah, the point goes outside. And then because we're talking about areas in between, and people don't believe in negative area, for this point to stay inside, I think you need it to be convex. As this kind of line goes around the edge. That's great. Okay, because people don't believe in negative areas, right? There would still be some version of this that would be true about, oh, the bit where you went outside the shape, that counts negative. And it cancels. But I guess that's why the word convex is there. So that like P inside C. And so that, as well as having P inside C, that means that like D is a subset of C. That's not great notation. Okay, independent of not only the size of C, but also the shape, as long as it's convex. Yeah, sort of a little bit Matt Livestream 2.0 disguised as chill maths, but felt quite chill. We got there in the end. What was the key? So reflection. Something I'm trying to get people to do as well, isn't it? Reflection. What was the key? So I got stuck here. Where I was not convinced that A and B could actually be the same thing. I also got stuck here with my plus or minus signs, and I should take something away from that. But I got stuck here, partly because I was being a bit lazy and not working out that this was absolutely true. So I have a question mark here, which I could avoid by, I wrote that because I was not sure this was true about the plus or minus signs. I should have checked that because then I'd have more confidence and I'd be a bit less stuck. It took me ages to work out that mod P here, the area P here, is not the thing that I'm trying to calculate. So I should have thought more carefully when I saw this definition. I could maybe have thought about P being like the inside area. I guess I wrote that down, but I didn't really think about what it was. I didn't mark it on my picture. So maybe I should have coloured this in. And then maybe I'd have realised that that's not what I wanted. that there's this keyword between. So I don't think I read the question carefully enough, partly because I'm talking to chat at the same time and doing this on the live stream, but I think that could have saved me from, for a long time here, I was trying to solve for P in my head, so trying to think, oh no, because I was going to have a statement like this, where the P's would cancel and give me some fact about F, which I guess would still be okay, because then I just plug it in. I guess then, yeah, that is true. I should have just done it. I'd have seen the P cancel, and I was worried that meant I was doing it wrong, but that's actually exactly what you're supposed to do. P is the area inside, so it's supposed to cancel out from the calculation so that you're left with the thing as the area between. So I think here this was too much in my head. So it needs to go from head to page. Write down what you're thinking. P is supposed to cancel. If in doubt, write down true things. I was nervous about whether they were true, but I should write down true things. And I should have actually written them down. Especially because on a live stream, you can't tell what's in my head. I have to write it down. Good, right, okay, learning. It's not always that I get to do a step question. It's like, what insights can I get out of having done this question? Right, good. Yeah, so in chat maths 222 a moment ago said, does integration of trig assume negative areas though? And we are integrating from trig functions, but they're all kind of multiplied together, and all the contributions that we're getting are actually positive, I think. That's not very convincing, but the point that I mean is this word between is really loaded. It imagines when you have two curves like this with one totally inside the other, then it makes sense to talk about what's in between. If you have two curves intersecting and crossing over each other, I'm not really sure what between means. Not the bit that's inside both of them, and not the bit on the outside, but then maybe it means this bit minus this bit, which probably is not what you would intuitively mean by between. Maybe the question should define between. Doesn't really have to if it's convex. Yeah, so F involves loads of stuff. What do I think F actually is? Yeah, so there's the relationship then between all of the integration that we're actually doing in the question versus actually whether that represents an area or not. F is kind of a tool along the way that I'm not sure F corresponds to any particular area at all. But it's an integral. It's something you calculate. It might be positive or negative, actually, I suppose. It doesn't really matter. It's just an integration. Whether or not the integration represents area, the positive quantity, actually between these two curves, is a separate kind of question, which you might have to worry about this kind of thing, or worry about which way round your two curves are, because the integration doesn't know that you have a big circle and a small circle, really, or whatever you're integrating around. Okay, good. Glad that fell out in the end. Two expressions. I've never seen this really before. Exaggeration. Probably have seen something like this. Two expressions. Don't really understand either of them. Trick is to set them equal to each other, cancel out the bit you don't like. Solve for that. I guess it's two unknowns, only want one of them, rearrange and solve, right? But I have unknown for what this is, would like to solve for it. Unknown F, and I have two equations. Algebra. Doing markup. I have two equations. Yes, my reaction immediately to seeing this was that these are equal and that I could therefore stop thinking about B, but actually the question really wants me to think about B. So it's a good thing they mentioned it down here as well. Otherwise I'd have had nothing to work with because I'd have crossed out all the B's from the question. The B matters, otherwise where's the stick? You know, where's the other end of the stick? Good, okay. Any requests? We're about to hit 4 o'clock, so maybe we're wrapping up, I'm not sure. Other math requests, if you like. Very happy with these area pictures. This one, the updated version, even better. And a saved copy. Saved, good. Okay, yeah, got it. We've had a quick look at power of a point. We've messed around with some areas. Let's set that running. Best run was various. Done step question. If there's no requests from chat for other sorts of maths that we should be doing, we integrated. We've had a couple of wins today, haven't we? We integrated sine to the 4 cos squared. That was a good one. Found the area inside as kind of star shape. Integration of trigonometric functions. That's what chill maths is. A-level integration. Right, okay. I should get better at step. I really should. I should be able to do these much faster, I think. Ooh. Yes, true. Areas. I think I've seen this question before. One more? One more. Okay, so this is a question like this. You've got function and the inverse function which you're integrating with respect to y. Why would it be less? Step stream. I've got to think for that, haven't I? Is it not just equal to AB? Am I being an idiot? Why is it not just equal? That's the integral of fx from 0 to a. Oh, what's b? Is f of a equal to b or not? Right, yeah, it doesn't have to go through that corner. Okay, so the integration might be larger. I'm a bit worried about this case though. What if the function goes up there? Then my integration from 0 to a of f of x will be huge, and my integration of inverse f from 0 to b will be tiny. It would just be this bit. Oh, integration will be huge. We might have some extra stuff if it's over or under. Okay, not as obvious as I thought. Okay, good. In the case is positive, oh gosh, was I supposed to be thinking about negative numbers as well? Ugh. Yeah, no, okay, these. Okay, non-zero numbers. In the case where they're non-zero, state a condition on a and b under which equality holds. Right, I think that is now f of a equals b, which is the thing I drew first, where the first bit of integration is the area under the curve, and the second bit is inverse means flip it over, and then integrate from 0 to b would give you the other side, this area, kind of under the curve after you flipped it, which is like, in this case, above the curve, because positive gradient. It's a good thing you don't have to prove this, just explain briefly. Good, okay. And now here's the bit I actually want to do, which is prove some facts with it. Prove some facts, right? I love step questions like this, where it's like, here's a big thing, give some sort of suggestions why it's true, maybe prove it for not this one, but a different question, I'd say prove it, and then just, here we go, here's x to the p minus 1. Right, here we go. So the trick here is going to be, well, I mean, we're just going to do what we're told, aren't we? Oh, this is not the kind of freedom that I was expecting. Yeah, because this is boring. Okay, I was expecting more freedom here. Yeah, okay, that's this and that's that. Good. Why does it say 1 over p plus 1 over q is 1? What's going on there? Oh, the inverse function. I should actually do the question, shouldn't I? So if y is equal to x to the p minus 1, then y to the that is x. So the inverse function involves this, where, right, so is this with 1 over p minus 1 is equal to 1 over, is equal to q minus 1? What is this? If and only if. I kind of get the inverse function is 1 over p minus 1, right? We do both sides to the power of 1 over p minus 1. And then for that to be to the power of q minus 1, I would need the powers to match up. So maybe I can rearrange this? I'm not very optimistic. Maybe I should be more optimistic. Yeah, because the 1s are going to cancel. Reasons to be cheerful. ones cancel, and you get this. And then divide both sides by PQ, and you'll get 1 minus 1 over Q minus 1 over P when you divide. So this is the condition in the question. So this condition has been written in a kind of weird way, but it is just so that these are inverse functions, and then we're good. Okay, equality holds. Verify that equality holds under the condition that you said before. What was the condition I said before? Oh, a to the p minus 1 equals b. That's the condition I had before. So if that's true, ooh, hey, let's see, I don't love that this has now got q's in it, which I have to deal with. Don't love it. It's brought in an extra letter of the alphabet, but well, yeah, dealing with that extra confusion rather than just having p on the right hand side. You know, morally, our function's just got p in. We could make this statement on the right with just p. We've translated it into q, so with this relationship, and then you can rewrite this relationship in different ways. But it's just an extra letter that we didn't kind of need. It's making me confused. It's confusing me for like no reason. Okay, so then if this is true, then a to the p is ab. So this is going to be a proof. And also b to the q, because it's an inverse function, is equal to a, because that's the inverse. No, b to the, what was the inverse supposed to be? B to the q minus 1 is supposed to be the inverse. So b to the q. Which looks mad, right? How would I invert it like this? But the answer is all of these things are the same. We're using the conditions that we had before, and that's just the PQ switch. I don't love it. So B to the Q would also be AB. So adding those things up on the right-hand side, we would have AB 1 over P plus 1 over Q. This is used to prove Holder's inequality. So that's actually good. This one here. Welcome to chat, Death Control. We've gone past 4 PM and we've picked up first time chat. Good. It's always nice seeing which maths it is that will get new people in chat. So say hi. In this case, Holder's inequality and functional analysis. Quite hard maths. Good. So basically a little bit like Twitch algorithm, right? Now I know if I put more functional analysis in the live stream, then I might get that community joining in. I need to get a lot better at maths, I think. What do I want to do here? I think I want to do something like sine, don't I? Sine would be nice. Oh, am I supposed to... Equality holds under the condition I said above. Yeah, I've still got the condition and then equality holds because this thing is just equal to 1. So maybe. Good, okay. Okay, so part 3. This is the bit that I actually enjoy, where you have to pick your own function, right? You have to choose your own battle. I can see arcsine and a b in here as well, which makes me think maybe I want to use sine. There's a pi over 2. Yeah. Maybe I want to use sine, and then I'll get an arcsine in here as well. We'll have to integrate arcsine, but I know how to do that. Ah, thanks for the follow. That is exciting because we're getting close to it, I think. You do streams as well. Cool, right. Death Control. Also streams maths on Twitch. If you have a schedule, put your schedule in chat. I'm vaguely aware of something called a raid. I'm not going to do a raid because I don't understand how, and because I think you're not currently live because you're in my chat. But hey, Nick, so you got to follow her right there. There you go. Community. There's also Cat Does Maths and Dr. Simon Clark if you're looking for other people on Twitch. Cat Does Maths does kind of study with me streams. Dr. Simon Clark sometimes does modelling climate stuff and sometimes does Warhammer, as you can find other people. Donkey Kong Country time. Oh, there you go. We sometimes do Minecraft, but I'm not very good at Minecraft, so not very often. 100 intervals. Maths, I don't think we're a category. I'm in just chatting. I don't know, but I've put math in my tags. 60 more integrals to go. If you like to see 60 more integrals from Black Pen, Red Pen done by Death Control, then it's a Twitch stream for you. I'm going to choose f of x to be sine. That's kind of my first guess. Arcsine. So I've got to integrate these things from 0 to A. If I integrate f from 0 to A, then I get, I'm being lazy, look, cos x minus cos x from how integration. I've got nervous. And I think when you integrate arcsine, you're just going to get, I can't quite remember how to integrate arcsine, but I can kind of cheat, right? That it's just this. Isn't it just this? It's math a category. Hey, can I edit categories live? Cool, right. We might be recategorizing the stream. Recategorized. Wait, chat just wants Minecraft. Anyway. Wait, I'm wasting my time. I should be just placing blocks. I had some bad times in Minecraft off stream recently. Exploring abandoned mine shaft, dug too deep, went too far from home, got lost, got out of control, ran out of torches, couldn't find my way back, died in a cave. Not good. Not good times. Bad times were had. I wonder if anybody uses these streams as like a way to learn maths, because you have to put up with a lot of other stuff in there as well. Like, this is going to be a good kind of like idea about integration, but it's buried in between like Minecraft stuff plus chat about functional analysis, and that's probably not useful for anybody. Or not all of that is useful for the same anybody. So you've got to choose your fights. I think I'm going to get the plus minus signs wrong, but I'm getting there, right? So I get 1/2 of minus sign of 2, but I want this. So I think it's plus. So I'm going to get B, arcsine B. I'm going to find out why. It's quite low stress because I can just go back and check. Is it plus on here? It is plus. Ah, I got all my signs right. Good. Oh, I get -1 though. Do I want a -1? Oh yeah, because I had a 1 over here as well. I should have spotted that when I was working that out. What's this? Even I enjoyed it. Minecraft, yeah, even Mary. Oh yeah, and Mary, sorry, for context, I remembered Mary has never played Minecraft. And was her maybe never seen Minecraft? Anyway, never mind. Okay. Oh, and the trypophobia. Yeah, because we're building a mega sponge, and they're quite bad for some people's phobias. Right, we're going to deduce a thing at the end. We're going to deduce a thing and then call it a day. I forgot about that. That was it. It was not the Minecraft surprise. It was the thing full of lots of tiny holes. Right, good. We're going to deduce one last fact, I think. I really can't think of anything except maybe to set B to be 1/t, right? That doesn't really look like it could possibly work. I get a choice of A. So in here, what do I want to do? I definitely want to set B to be 1/t, because if I don't, I've got no chance of doing anything sensible with this arcsine. And good, it's still on the large side of the integral, so we're good. I'm going to multiply both sides by t, and that'll give me, so this root 1 minus 1/t squared. Write it down. Learning. That'll move to the other side to get a minus sign now. It'll be multiplied. I'm going to multiply both sides by t, so that will give me this on the other side. But I would also get, well, let's write down a true fact. I'm learning. Look at me learning. A/t less than 1/t arcsine 1/t plus root 1 minus 1/. I'm going to have to do it again, look, because I've gone back a step. Minus cos A. The only question is going to be what I want the value of A to be. So multiply both sides by t and rearrange, and you get A minus root t squared minus 1. So I've got A over there, that's a clue, and I've got t cos A, so I can't hate it. I don't want that sort of term at all. Arcsine inverse t. That's it. So I just need to kill both of these. We want to remove these. Does A equals 0 do it? Pi/2? No. Have I got a number on the right hand side? Have I got anything? Oh, I've got t. I wouldn't mind a t. Actually, so not quite remove. I wouldn't mind this being 1. So can I find a value where these are both simultaneously true? That this thing I want to go away, and cos A, I would like that to be 1, so they get exactly t on the right side. Can I think of something that satisfies both of these simultaneous equations? Simultaneously, the answer is yes, I can. A equals 0 works. So that's lucky, isn't it? But I can solve this second equation to work out the exact value of A. And then miraculously, it also works in here. Maybe not miraculously, maybe just I've successfully thought of the same thing that the examiner thought of, but yeah, we get onto this. Maybe I'm better at step than I thought, or remembered. Not sure I've done that one before. Good, right, okay. Promised one more step question, did one more step question. What's the step stream? I think I'm going to stop there, because it's 4:15. Thanks for watching. Thanks to people who've subscribed. Do check out Death Control doing 100 integrals. Welcome to the stream, Death Control. Do check that out. If they know when they're going to be live, they can let us know in chat right now. I'm going to be live next Sunday for more chill maths. You can catch me at my work stream if you're interested in maths admissions test stuff. We do a stream at Oxford for that sort of thing. Quick, let's get rid of the step branding for this bit. There we go. We do a work stream for Oxford maths stuff up on Thursday. But otherwise, yeah, okay. Death Control might be doing integration on Saturday, so you got so many choices of bits of maths to find out. Right, cool. See you around. Have a good weekend. Bye, everyone. Oh no, there's a professional streamer in chat, and they're going to find out that I don't know how to stop streams. Wait, no, I have a thing. Okay, that one.